Okay, in this video we're going to show how to use COMSOL multiphysics to model the strain in a diving board with somebody standing on the end. This is going to be a 2D problem, so I'm going to click on 2D, click on Next. Then this is going to be a structural mechanics problem, so I go down to structural mechanics, click on solid mechanics, and then also click Next. And this is going to be a stationary problem. We're not going to do the transient problem right now. So stationary problem, and click on Finish. So that sets up my model here. First thing I need to do is define the geometry. So I'm going to right click on geometry and create a rectangle. Of course, I could also go up to the geometry toolbar here and select rectangle. So let me just go ahead and do that. Sometimes what I like to do is select the rectangle. Let me just delete that first one. I can select this rectangle and fix up the dimensions later. So this rectangle, we want to have a width of 3 meters, so that's going to be 3, and we want it to have a height of approximately 10 centimeters, so 10 e to the minus 2. And the corner can be 0, so we can go and build this and zoom extents to get this in that shape. So this rectangle is going to have points at each of these corners, but it's not going to have any points in the center, and we're going to need to have some points there so we can apply forces and constraints. So I'm going to introduce a point here at the 1 meter mark. So in order to do that, I again go to Geometry, right click, go to Point, and then I'm going to put the point at an x value of 1 meter and a y value of 10 e to the minus 2, which is, y value of actually 0. Click there, and that's going to allow me to support this beam at this location, and I already have a point here. When we think about standing on the end of this board, I'm going to suggest that we put a point here at 2.5 meters and apply a point load. So in order to do that, I need to make another point, the point in there, and this is going to be at x is equal to 2.5, and this is going to be on the top, so y is going to be 10 e to the minus 2. And click on Build. Okay, so I have that point. So this allows me to apply constraints and forces to those areas. Okay, so that's what I need to do next. For materials, instead of choosing a material, I'm going to define my material parameters under structural mechanics. I looked up fiberglass. It's on the order of 70 or so gigapascals as a Young's modulus and a 0.22 for the Poisson's ratio, so that's what we're going to use there. So I can go to my linear elastic model and go down to Young's modulus and use that as user defined, and type in 70 e to the 9 pascals, that's 70 gigapascals, and then from Poisson's ratio I'm going to also make that user defined, and that's going to be 0.22. And I don't believe the density needs to be defined for this problem. So we'll leave that free. If we need to, we can come back to that. So we're not dealing with any initial values, we're just dealing with constraints. So I need to constrain some of these points, so I go down to Points, and we have the choice of Fixed Constraint. So Fixed Constraint means that it's constrained in all directions. Prescribed displacement allows us to prescribe displacement or fix it in one direction, and point load would allow us to fix it or to apply a load into that point. So let's first go to prescribed displacement, and so first thing I'm going to do is choose point 1 and add that to the model, and then I'm going to prescribe that motion to be prescribed at 0 in the x and y directions. Okay. Then I need to make another prescribed displacement. So we go to Points, Prescribed Displacement. Now I can click on 3, add that to the model, and that one I'm going to just fix in the y direction. I'm not going to let that go up and down, but it can slide left to right. Then I need to apply a point load at my other point where a person will be standing. So in order to do that, I go to point load, click on number 4 point, add that to the model, and use this y direction force to apply and load. This is going to be minus 660 newtons, which is 150 pounds, and that means that in the minus direction, so it's going to be down. So we can expect this to bend down like that. We can now go to mesh and use user-controlled mesh, and we have a free triangular. We can build that, and now we have our mesh. Okay. So under study, we should have just about everything we need. We don't need to say anything about stationary, and so we can compute this. So as you could see, that it didn't need the density to be input in there. The density must be part of some of the equations. We could have taken a closer look at some of the equations. So what you can see is that we have a displacement of e to the minus 4. It's fairly low. It's very possible that the dimensions aren't reasonable here. Another thing that we sometimes need to look at is the actual thickness of the thing. So thickness is the distance into it, and we're going to put that at about 1/3 of a meter, so put 0.3 meters, and then we can solve this again. That probably won't make much of a difference, but solve that. Okay, so it's approximately just about the same, maybe a little bit more by having that designating that thickness. Okay, so part of what we wanted to do was to be able to, so this is displacement, but part of what we wanted to do was to show this in terms of strain. So we can go and look at different types of expressions. Okay, so we can change the expression by clicking here, go to solid mechanics, go to our strain tensor, and then pick our x component of the strain, our ex. Okay, so what you can see now is our strain map, and we can see we have high tensile strains on the top and high compressive strains on the bottom. If we wanted to find the strain at a particular point, what we need to do is need to add what's called a cut point. That's done in data sets, and we go and add a cut point in 2D. Cut point 2D means it's a point that we define its 2D location. So that's done here. Let's say that we want to do this at 1 meter, and we want the y to be 10 e to the minus 2, so that's again at the top, and then we can plot that, and then we get that point right here. Okay, so if we want to find the value of strain at that cut point, we need to go to derived values, right click on that and do a point evaluation, and the point evaluation, we go up to data set and we select our cut point data. If we want to do strain, then we need to change the expression, choose solid mechanics, and then find our strain tensor. It's right here, and the x component of strain is right there. We add that. Okay, we have that right there, and then we go ahead and click equal sign, and that gives us the value of strain at that point right down here.